Next up, we take a look at some of the details of Ethernet technologies. So as we saw in early lectures, we use untwisted pair cables. So this is the most common media type in local area networks. These are usually 4 pairs of copper wires twisted together in pairs, and it comes in, as we saw, numbered categories from 1 to 8. Um, Typically see Cat 5 and Cat 6. You can also have fiber optic cabling that uses thin strands of glass, or the cheaper ones use more plastic to carry pulses of light for long distances and at very high data rates, much more than um, electrical cables. You may have seen coaxial cable. That's still pretty much what's used for your cable TV connection. That might also go to a cable modem, and that used to be the main Ethernet connection a long time ago, but it's now obsolete as a LAN, local area network medium. So there are two main ways of transmitting signals, and that's baseband and broadband. Baseband sends digital signals as a pulse of electricity or light, like a 1 and a 0, or um, things like that. So a 1 is just, let's say, a high electrical voltage or the presence of light, and a 0 is a low voltage or the absence of light. So this is sent at a single fixed frequency, like 100 megabits per second, and no other frames can be sent along with it. So compare that to what you would use in a cell phone, for example. Cell phone uses broadband or analog techniques, and so it might encode a 1 as a frequency of, let's say, 2 gigahertz, and a 0 as a signal with a frequency of 2.4 gigahertz, let's say. It's just examples. And so what you really have are not just like low voltage and high voltage, but you have constant signals going out. They're analog signals, and they use something like frequency to encode ones and zeros. Actually, that's not what happens. You actually have bands or different frequencies, different ranges of frequencies in which you operate, and so you have signals flowing at particular frequencies, and then each frequency actually represents a channel of data. So Wi-Fi, for example, has, I believe, 11 channels, something like that, out of which we just use 2 most of the time in the United States, and then other countries will use other channels. Okay, so these are the two main technologies that are possible. If we're talking Wi-Fi, we'll talk broadband, but there's not much of that in this course. For the most part, we'll use baseband, and you'll see this term base show up in some of the terms, some of the abbreviations. So that when you see base, it's a good chance it's talking about baseband. That is, signals are going out as ones and zeros, single frequency, and just one thing happening at a time. If you have 2 things happening, they'll collide most of the time. So of all the technologies that we will look at, the Ethernet LAN technology is the most common, the one that you'll see the most of the time, and the only one pretty much that we'll use in this course in the lab. This supports a broad range of speeds. 1 megabit per second is still around. You can probably, the slowest you'll probably see these days is 10, and then 100 is what we use in the lab, and that's also pretty common. You can go up to a gigabit per second, and then maybe even up to 10 gigabit per second these days. You might find hardware that supports this. You can operate it in physical bus topology or a physical star topology. Ethernet can, and logical topologies can be bus or switched. Most often these days it's star physical topologies and switched logical topology. Those are the ones that make the most sense at this time. So You've probably seen this, that most network interface cards and hubs and switches can operate at multiple speeds, but usually they go down to the lowest speed on a particular connection. So these days what you will see is 10 megabit per second, 100 megabit per second, and 1000 megabit or 1 gigabit per second. The basic technology that's connecting, that's behind the NICs, the electronic circuitry and all that, is pretty much the same. Some of them work faster, some of them are slow. So we looked at Ethernet. We looked at frames and the fact that each frame has a destination MAC address and a source MAC address, and each computer, or we'll refer to the computer on a network as a station, and each station has a physical MAC address. Each station on a router also, each interface on a router also has a physical MAC address, so it's something to keep in mind. And each MAC address is a 48-bit number. 48 bits, if you divide by 8, will give you 6 bytes. And remember, each byte is 2 digits, 2 hexadecimal digits, which gives us a total of 12 hexadecimal digits. And chances are you've seen this on your smartphones. If you go into settings, you will see a Wi-Fi MAC address and also a Bluetooth MAC address, chances are. When you get a frame, and this is true of pretty much all devices, whether it's Ethernet or Wi-Fi or Bluetooth, the incoming frame destination MAC address has to match the network interface card's MAC address that's burned into memory. Either that, or the MAC address, destination MAC address of the incoming frame has a broadcast address of all ones, or that's binary ones, or hex Fs. F is just 1111, so 2 Fs is 8 ones. Okay, and so you have 6 bytes or 6 sets of 8 ones, so 48 ones will indicate that it's a broadcast MAC address. So once a frame is processed by a NIC, these frames, you open them up and you get the packet that's inside the incoming frame, and you send it up to layers of software, and the next one up is the network protocol for further processing. We'll talk more about the layers and things later. Some more details of Ethernet frames. There are actually 4 different formats for frames depending on the protocol used to send the frame, but in this course we will just consider one of them, TCP/IP, which uses Ethernet 2. So that's the only kind of frame that we will look at, and this is the format we will use. So this is the format that Ethernet 2 has. The first 6 bytes are going to be the destination MAC address. The next 6 are going to be the source, where the frame came from. You have a 2-byte type quantity, followed by the actual data that you're intending to send, and then after that comes the frame check sequence, or the frame trailer, or the cyclic redundancy code. That's 4 bytes. It's a 4-byte summary of the rest of the data in the frame. And so remember, this is used to check and make sure that the frame was sent and then received the same way all of the data that was sent was received. So here's a deeper dive into the structure of Ethernet frames. So each frame starts with a destination MAC address, so it starts right here. But just before that, there is a preamble. So there's 7 octets, and it's usually AA. I believe it's just AA because A is just 1010. And so it's like a square wave sort of signal, followed by a start of frame delimiter, which is just AB, and that signals that the next bit after the B set of 4 bits will be the destination MAC address. So this preamble just tells us that we have just tells the receiving NIC what speed it's being sent on essentially. And then you figure out the speed and then you adjust, and then you get to the starter frame delimiter, which is just 1 byte or 1 octet, and that tells you that the next bit is going to be part of the MAC address of the destination, followed by the source, followed by a tag, followed by, actually we don't even have a tag, we have 2 octets for Ethernet 2, we don't use this, and then the data, which is called the payload, followed by the frame check sequence, and then after that you have to have an inter-packet gap, that is basically 12 bytes of silence. So that's just a way for the NIC to recover 12 bytes of nothing, followed by maybe a preamble of the next frame and so on. Okay. So Ethernet uses what is called CSMA-CD, or Carrier Sense Multiple Access with Collision Detection. And this is actually the collision detection part is for historical reasons because it was used before, but it's been carried forward in the current generation of Ethernet devices too. So the carrier sense part, what does that mean? It says listen before sending. You have to hear silence. So if you have multiple Ethernet devices on a single connection, remember that's just 4 pairs. If there's all kinds of devices connected and transmitting on those wires, they have to make sure that there's nothing before they send. You have the MA part is multiple access. So if 2 or more stations on the Ethernet connection hear the silence, it is possible that multiple stations may transmit at the same time. So that's the multiple access part. There's multiple stations connected to those transmit signals, transmit wires. If you send out a signal and there's another station transmitting at exactly the same time, you say that a collision has happened, and this can be detected by the NIC because the signals will be abnormal in some way, and so there's a collision detection part as well. And so if you do detect a collision, all the stations that are involved in the transmission must retransmit, and there's a lot of logic that goes into making sure that they don't retransmit at exactly the same time, or they try not to. So you don't wait for exactly 1 second and try again. No, you try different. You try a random amount of time before you retransmit, things like that. Okay. So collisions are possible when you use a hub. So remember that when you send something into a port on the hub, that hub is just sending that signal, same signal out on all the other ports. So it's not like a switch is not, switch behaves very differently. So hub has a logical bus topology, whereas a switch has a logical switch topology. If you use hubs, you have to be ready for collisions. And so the idea is that a computer over here sends a signal out, it goes out on all the ports, one of them being another hub. This sends it out on all the ports to the switch and to the hub. And let's say a computer over here sends out a frame at exactly the same time. Well, it will get to here, and so on the hub 2 will get 2 signals at exactly the same time, and it'll do some kind of addition or something in the electronic circuitry and send out the sum of those 2 signals out of all the ports, and that's going to be a collision that will be detected at the switch certainly, and at other NICs in the network. So all the other computers will detect that collision, and the original sources, the one over here and the one over here, they will also detect it, and then they'll decide that you have to retransmit at a later time. So whenever you have a hub, you have a collision domain. That's the important thing, is it's possible for 2 computers, 2 stations on the LAN to send out frames at the same time, and their NICs will detect that. So you have a collision domain over here. Switches do not form part of the collision domain because they use switch topology, logical switch topology, rather than the bus topology. So this is a collision domain, this is a collision domain because they both have hubs. So devices connected by a hub hear all signals generated by other devices on the hub, and so the extent to which these signals in an Ethernet bus topology are propagated is called the collision domain. And so whenever a station sends out a frame, it is possible, if you have a hub, for collisions to happen. And so remember, I'm going to scroll up, that switches, on the other hand, have a star topology, even though these have star topology too. In these wires, you can only have, if you have a star topology going to a switch, there's only, unless you're talking about broadcast, you only have a single pair of stations communicating, unlike a hub where you send a signal, goes out on all the ports. So let's take a look at the frame check sequence, which was at the tail end of every frame. And so the idea there is that Ethernet is a best effort delivery system. So unlike when you send mail through the post office, well, usually they deliver it, but pretty much you just hope that it gets there. There usually isn't an acknowledgement of receipt of that piece of mail unless you specifically ask the recipient to send something back. So when you send something in the mail, you hope it gets there. Most of the time it does, but there's no way to find out immediately, although these days you can get a tracking number and things like that, so it's a little different now. Not the best analogy. Network protocols and applications that are higher level besides Ethernet are what are responsible for ensuring that things are delivered. What you can detect at the Ethernet level is collisions. So if you detect a collision and the Ethernet circuitry can detect that, then you automatically retransmit. Okay, and then Ethernet devices can detect damaged frames due to burst of interference, like a power cord next to an Ethernet cable, and then this surge or something can change the bits in a frame. And so that's what this frame check sequence, or the trailer of a Ethernet frame, is used for. It has error checking code called CRC, or cyclic redundancy code, or cyclic redundancy check. And so when you get a CRC code, you can compute out what it should be. It's just it's a very simple binary operation, and then you can compare that to the frame check sequence, that is the CRC code that was sent with the frame, and if they are not equal, then you know that the frame was damaged, and so you just discard it. You don't notify the sender that the sender should retransmit. Okay.